You don't think so? Okay. Well, we're in the middle, towards the end of an example problem. So here's the example from last time. We had a hinge on the ground connected to two slender rods. I numbered them 1 here and 2 here. The masses are the same. They're each 5 kilograms. The lengths are the same, each 1 meter. The angles are 45 degrees here, and this is a right angle. At this instant, the angular velocities are both the same, negative 10 radians per second. And it's negative, so it's clockwise. They're both the same, and I stressed last time that whenever you're talking about rotational things, you're talking about that rotational quantity relative to the coordinate system, to the ground, not to some body it's connected to. So what that means is both of these are, their orientation is changing at 10 radians per second clockwise, and that means that this thing is just all as a single piece rotating like that. But we don't know what the angular acceleration is. So at this instant, that angle of 90 degrees is staying constant as the thing tips forward. If you think of this as sort of like a simple, as the legs of a person, this person is tipping over onto their face. Unless they have really terrible knee hyperextension and then they're tipping over onto their back. Okay, so, and there's a force. So you're applying a force at the knee of 100 newtons, and we want to see what that does to the accelerations. All right, so we isolated member 1. Does member, yes? Nope. That would just be like not enough information. I suppose if you saw that on homework and it didn't say anything, you'd assume that it was 0. But and we isolated member 1. Does it have a fixed point? Yes. And so we didn't have to use Newton's second law. So we don't have the acceleration of the center of mass as a variable, and we only use the rotational equation. So we get one good equation for member 1. And that equation was negative 0.7071 F12x plus 0.7071 F12y minus 1.6 repeating alpha 1 is equal to negative 53.37. And then we isolated, and that's all we get out of that because we only have the rotational equation because of the fixed point. And then we isolate member 2. Does that have a fixed point? No. You might think like, yeah, it's connected to member 1, but that point isn't fixed. It can move in space. So we will use a constraint equation for that, but it's not a fixed point. And so we did have to use Newton's second law, and we did have to introduce the acceleration of the center of mass as a variable. And so that gives us three good equations, and those are negative f12x minus 5a 2x component. That's the x component of the acceleration of the center of mass is equal to 0. And then the y component equation is negative f12y minus 5a2y is equal to 49.05. And then the moment equation says negative 0.3535 f12x minus 0.3535 f12y minus 0.416 repeating alpha 2 is equal to 0. And those are our four equations after we're done with Newton's laws. We have four equations, but variables we have 1, 2, 3, 4, 5, 6. And so we need two constraint equations. And it turns out it's always going to come out as a perfect match if this goes right between the number of variables that you have above the number of equations. So the number of equations you need and the number of equations that come from the joint constraints. Okay. So the joint constraint we'll call this joint. So let's call that A, B, C. And so our joint constraint is going to be at B. And it's going to say the point B on member 1 has the same acceleration as the point B on member 2. We already did member 1. And we got that the acceleration at that point B was equal to negative 0.7071 alpha 1 minus 70.71 for x, and then positive 0.7071 alpha 1 minus 70.71. Okay, so that's the acceleration vector of the point B on member 1. And now we're going to member 2. Okay, so what's our strategy for expressing the acceleration of B on member 2, given that it doesn't have a fixed point? Member 2 doesn't have a fixed point. Yeah. You use watermelon equation to, so we're going to use two things here. First, we're going to express the acceleration, well, use the acceleration of the center of mass of 2. Those are variables already, okay? And then we're going to add to that its relative motion, the acceleration, assuming that the center of mass is fixed, the acceleration of that point B using the watermelon equation. Okay. So You can think of this as, so the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of 2, plus the acceleration of the center of mass of 2 relative to the ground. Acceleration of center of mass of 2 relative to the ground. This one is already in our list of variables. That's A2. And this one is just circular motion. So that's alpha cross R plus omega cross quantity omega cross R. Okay, so the acceleration of B, according to member 2, is A2 plus 0, 0, alpha 2, and I'm just using all variables that we've already defined, crossed with the R vector. So if you're using circular motion, assuming that the center of mass is fixed, the R vector goes from the center of mass to the point B. Okay? So that's 0.5 times cosine and sine of negative 45. So that's 0.3535, negative 0.35350. And then plus, our omega is what was given at the start. So that's 0, 0, negative 10, crossed with the quantity 0, 0, negative 10, cross, same R vector again. This one comes out to be 0.3535 alpha 2 for X, positive 0.3535 alpha 2 for Y. And this one, once you multiply it all out, that's just numbers, and it comes out to be negative 35.35 for X, positive 35.35 for Y, 0 for Z. And so if you add it all together, you get an acceleration of that point B that's equal to, for the X component, A2X plus 0.3535 alpha 2 minus 35.35. That's the X component. And the Y component is A2Y plus 0.3535 alpha 2 plus 35.35. And then there's no acceleration in Z. This is just a planar problem, so I'm going to just leave it to 2. We can only do planar linkages. Why can we only do planar linkages? Well, we can only do planar rigid body problems. So since this is all built around rigid body kinetics, you know, that's a restriction that we just absolutely have. We can only do 2D problems of rigid bodies for now. Okay, so the constraint then says that those accelerations have to be equal. So you can write this out as, I'm probably writing this all out more times than I need to, but at least this first time I just want to be, clear about what we're doing. So first, on the left side, I have the acceleration of B on member 1. So this is what we got on Wednesday. Negative 0.7071 alpha 1 minus 70.71 for X. And then for Y, we have positive 0.7071 alpha 1 minus 70.71. And we're setting that equal to what we just calculated, the acceleration of B on member 2. So that's A2X plus 0.3535 alpha 2 minus 35.35. And then the Y equation, A2Y plus 0.3535 alpha 2 plus 35.35. And that gives us our 2 more equations that we need. We had 2 more variables than we had equations before the constraint. We needed these 2 more equations, and so I'll just rearrange these, put them in a form where we can use reduced row echelon form. And so the first one says negative 0.7071 alpha 1 minus A2X minus 0.3535 alpha 2 is equal to 35.35. And the second one says 0.7071 alpha 1 minus A2Y minus 0.3535 alpha 2 is equal to 106.06. We didn't introduce any new variables, so now we have 6 equations and 6 variables. And now we have a system we can solve. Yep. The the left side. Okay, so what I did is, so we're saying that this point, there's a point on member 1 that's at B, okay, and there's a point on member 2 that's at B. And if they're connected by a pin joint, then the accelerations of those 2 points have to be the same. That's what it means to be connected by that pin joint. Okay. So first we isolated member 1. We did this on Wednesday, so I didn't do it here. But first we isolated member 1, and since member 1 has a fixed point, all we had to do was use circular motion to figure out the acceleration of that point B on member 1 around the fixed joint. So we got that. And then we went to the second one, which doesn't have a fixed point. And if you don't have a fixed point, you have to express that acceleration in terms of relative motion. Okay, so yeah, that's right. So this one here is just the expression for the acceleration of that point B on member 2. But then once we got that, we just, we did it for member 1, did it for member 2, and set them equal to say their accelerations have to move together because they're locked together. Okay. And so to solve this, I'll set up an augmented matrix. We're going to have 7 columns. and 6 rows. The rows represent the equations. And the columns represent the variables in whatever order you want to do. I'm going to do F12X, F12Y, alpha 1, A2X, A2Y, and alpha 2, and then the last one is the constants. And then I've already written all these equations with the variables on the left and the constants on the right. And so now all I have to do is go through these equations and read off the coefficients and put those in the matrix. So F12, so let's see, I have it written here. F12X for the first equation, that's negative 0.7071. F12Y, positive 0.7071. Alpha 1, negative 1.6 repeating. And the constant is negative 53.37. Equation 2, F12X is negative 1. A2X is negative 5. 0 for the constant and everything else. Equation 3, F12Y is negative 1. A2Y is negative 5. And the constant is positive 49.05. Equation 4, F12X is negative 0.3535. F12Y is negative 0.3535. Alpha 2 is negative 0.416 repeating. The constant is 0. Equation 5, alpha 1 is negative 0.7071. A2X is negative 1. Alpha 2 is negative 0.3535. And the constant is 35.35. And then equation 6, alpha 1 is 0.7071. A2Y is negative 1. Alpha 2 is negative 0.3535. And the constant is 106.06. And then reduced row echelon form gives you F12 is 72.51, 92.03, and that's newtons. Alpha 1 is 40.30 radians per second squared. The acceleration of the center of mass of 2 is negative 14.50, negative 28.22. And the angular acceleration of 2 is negative 139.59. Any questions about the calculations or anything? Okay, so let's interpret what we have. This is, I think, cool. So what we figured out is, if this was a static case, you know how to calculate the reaction forces. But we figured out that with this thing moving that way and with this force applied, what the contact force is between member one and member two. Okay? There's nothing about the combination of the weight and the force applied here or anything like that that would let you get like an intuitive idea of what that contact force is going to be really. But we figured it out, you know. And if this was a biomechanics problem, you know, if this was something that, say this was something that happened in a car accident a lot, you know, like you knew that the knee hit the dashboard with this much force, we could use this calculation to figure out what kind of forces the ligaments are under, what we could change to make it less dangerous, that kind of thing. And then the second thing we figured out has to do with the motion that results. We didn't, you know, we don't calculate anything about the angular velocities because that doesn't have to do with the forces applied at that instant. Only the accelerations are determined by the forces. But we figured out that body one has a counterclockwise angular acceleration, and body two has a clockwise angular acceleration that's quite a bit bigger in magnitude. So let's think about what that says. Okay, so this force is going to make body one have an angular acceleration this way, right? Counterclockwise. The direction makes sense with the force. But what isn't so obvious, and what we figured out, is that the angular acceleration of two, which also is clockwise, and that the direction makes sense, but we get a much bigger angular acceleration of body two snapping that way from this force than we do of body one snapping that way. You get this sort of like whiplash effect. So this is a really simple linkage problem. You know, you can't make them much simpler than this. And that part's a little disheartening because it took us 2 classes to do this. But the cool thing is, I mean, without changing any of the technique, you can imagine how you could apply this idea to like any kind of multi-component machine. If you're going to get more than a small number of members, it wouldn't be practical to do it by hand. But it's a very algorithmic sort of approach. You know, it's not too much of a stretch to imagine that for whatever your application is, you could write a pretty simple program, as computer programs go, to do this calculation for you. You know, and then we calculated this at a single instant. Well, we know something about the accelerations of these points. What if we wanted to know what happened over the next 10 seconds or something? Well, as long as we know the forces at each of those instants, we calculate these accelerations. You can integrate those numerically. You know, your program can just do the integration over time, calculate what the angular velocities are at the next instant, and then use all that stuff as inputs for the next instant calculation. You know, run this through your program. This is all a loop. You know, by hand it takes forever, but on a computer this loop is instantaneous. Calculate it at 0.01 seconds later, figure out what the accelerations are, integrate again, go to 0.02 seconds later. And doing that, you can actually do simulations of what happens over the whole process. Yeah. Yes. Yeah. Right. And so, like, when I give this to you on tests, what I often do is I'll just say, give me the, like, don't solve anything, just give me the constraint equations for this one joint, you know, or draw the free body diagrams of the different things and then write out the constraint equations. So that, because otherwise, even to do like the simplest problem would make you work sort of fast in a 50-minute test. so there's not much I can do there. But any questions about that one? Yes. Yeah, the way to do it is um, for each body, this one has two, but each body in the linkage, um, use Newton's laws, go through the rigid body problem steps. So if there's a fixed point, you don't use Newton's second law. If there's no fixed point, you do. Get all the equations from Newton's laws. Every body with a fixed point, it'll give you one useful equation. Every body with no fixed point will give you three useful equations. So list those all out. And then when you're done with that, you'll have more variables than equations, okay? And the difference there will be the number of constraints you can get from the joints connecting bodies. And then you just go to the joints. And then, different joints put different restrictions on the motion. A pin joint always just says the accelerations have to be the same at that point. And when you go through those, you'll finally have a system with the same number of variables as equations, and you can solve it with reduced row echelon form. Any other questions? Okay. Let me show you the next example, the last example I want to do. And then I'd be happy to, when you guys start having questions about homework problems, I think I'm not even going to start this today, but let me just talk about it for a second. So the next example, we have a pin joint there connected to a rod. And then that rod is connected to this one by a pin joint. And this second one, it's not connected to the ground by a pin joint. That would be a structure. It wouldn't be able to accelerate. Instead, this can move freely in a slot. And we'll say at this instant, this angle 60 degrees, this angle 60 degrees, so it's an equilateral triangle. I'll call this body 1 and body 2. And we'll say that the length of 1 and the length of 2 are both 3 meters. And the masses are both 10 kilograms. And at this instant, both of these two members are at rest. So the angular velocities are 0. So it's starting from rest. And then we're applying this 600 Newton force this way. And I'm going to call these joints, this one A, B, and this one C. And for this problem, let's say that instead of just generally figuring out the angular accelerations of the bodies, we want to figure out specifically what's the acceleration of that point C, that pin C in the slot. Like if this was, why would we want that? If this was part of what's that called on old style railroad cars that turns the wheels, the crankshaft? You know what I mean? This thing moves around and turns the wheels in old timey movies. So say that this was connected to, somehow connected to like a gear or something. It's turning the gear. And we want to be able to calculate at this instant what the acceleration of that point. So we want to calculate what's the acceleration of the pin in the slot at C at that instant. Okay, well, let's just sort of look at this and see if we can figure out how many variables, how many constraint equations we're going to get. Okay, so first member one, how many useful equations are we going to get out of member one? Just one, because there's a fixed point. And for variables, we're going to have, so there's a reaction force here, but just like the reaction forces at the fixed points never appear in our initial system of equations, just like it didn't last time. And so the variables we get in this one equation for body one are the force on 1/2 at this pin, so that's two variables, and then the angular acceleration of that body. So three variables in that one equation. Okay. So we're behind by 2 so far. And then we go to the second one. How many equations are we going to get? 3, because there's no fixed point. It's as simple as that for figuring out, even though there's some more complicated stuff going on here. So now we have a total of 4 equations. What variables are we going to introduce? Well, just like before, we're going to introduce the acceleration of the center of mass and the angular acceleration. Okay, so that's 3 more variables. Okay, so that would be 6 variables. But now we have one more. This pin and slot joint applies a vertical force, like a normal force, to that pin, right? And so that the magnitude of that force, we'll call that n or something, is a 7th variable. Okay. All right, so we have 4 equations and 7 variables. So in this case, it looks like we actually need 3 constraint equations, not 2. Okay, is that going to be a problem? It's not, because we're going to have the 2 constraint equations here, just like we did in the last one. But we're also now notice that this pin is confined to only accelerate in the y direction. So our 7th equation is we're going to come up with an expression for the acceleration of that point C. And then we're going to say that the x component of that acceleration is equal to 0. Okay? And so we'll get 2 constraint equations here, 1 more here. We'll have a system of 7 equations and 7 variables. So it's cool how it works. I mean, if this wasn't here at all, that wasn't connected to anything, you know, this was just out in space, we just basically have a sideways version of the problem we just did. But if you add a, you know, another joint, another requirement for the motion, it adds more variables because there are forces in that joint, but it also adds more constraint equations that are available to you, and they always match up. Question? Yeah, to calculate the acceleration of this, we'll have to use relative motion and say, you know, AC relative to ground is equal to AC is equal to AC relative to the center of mass plus A center of mass relative to the ground. Yep.
Are we assuming that C is frictionless?
Yeah, in this case. It doesn't change the sort of approach at all, though. So, like, for example, let's say that there was viscous friction in there, you know, that it's full of oil or something. And so Well, the force that's applied by the oil to this thing is proportional to how fast that's moving. So we just come up with an expression for how fast this is moving based on the angular velocities. I guess the way it's set up right now would be 0. And then we just put that in as another force. Since we already know the angular velocities, it would just show up as a number. Same thing here, like if you wanted to include some friction there, you might just include that as like a moment on each one of those, a small little extra moment. And if you knew that as a number, you just add that in and it doesn't change the process at all. Any other questions? Okay, that's it. Have a good weekend.